Afternoon. So my name is Michel Baudouin-Lafont. I'm from University Paris Sud in France. I'll be chairing this session called Alt.Modalities, where we'll be on for a wild ride, going from dancing fonts to audio and sonic interfaces and to inquiries into the depths of our brain. Before we start, I have an announcement. For those of you who used the paper program, this session will not be repeated tomorrow at 10:40. As the program would have you believe. So instead, tomorrow morning we have the joint plenary session with the HCOM conference, and the session at 10:40 is the second one that appears in the program. So without further ado, we're going to start with the first of the 5 talks we have in the session. And so I'll give the floor to Danielle for designing and evaluating Livefonts.
Okay, thank you. My name is Danielle Bragg, and I'm a PhD student at the University of Washington. And today I'll be presenting some work done in collaboration with Shiri Azenkot, Kevin Larson, and Bessemans, and Kalai. The title is Designing and Evaluating Livefonts, and here we have a meta title of sorts for you with the word Livefonts written in a live font. So to give you a feel for the problem that we are trying to address, suppose this is your personal device, it might be your smartphone, and you have very blurry vision. Can you see what this says? It's pretty hard. What many people with blurry vision do is they zoom in. But then you lose the complete text that you're trying to read, and as a result, you're basically forced to pan around the screen, which can be very cumbersome and difficult. So much so that many people abandon the task entirely. And reading small text like this is a big problem for millions of people. So there are hundreds of millions of people around the world who are visually impaired or have low vision, where low vision is defined as vision that cannot be fully corrected with glasses. And furthermore, as we get older, everybody's vision begins to lose the ability to focus, meaning that we'll all end up with reading glasses eventually. And to make matters worse, we're moving towards a world of personal computing devices, which have limited screen space and often force text size to be small. The solution that we propose in this work is Livefonts. So Livefonts are scripts that redesign the visual representation of each letter using animation to distinguish characters from one another. So to give you some intuition for why Livefonts might improve legibility, let's consider the script on the right. So it consists of traditional letter forms, but each letter, A through Z, also has a unique color and animation combination. So as the text comes out of focus, letter shape becomes imperceptible, meaning that traditional text is not legible, but the colors and animations are still visible, so the script on the right can still be read. Here's another example where the live font does not resemble traditional letter forms at all. And you can see that under blur, it's still at least comparably more legible. So live fonts are a subcategory of smartfonts, which we presented at UIST last year. The idea of smartfonts is basically to have every traditional letter form replaced with a new letter form to improve the reading experience. So they're one-to-one mappings, replacing each traditional letter form with a new character, and as a result, they preserve spelling, grammar, and punctuation. But of course, we could do work to replace strings or entire words with alternate characters as well. Past smartfont designs explored color, shape, and spacing variations, and here are some examples of alphabets of possible smart fonts. Live fonts add animation to the design space, introducing another channel that can help differentiate letters. So in this work, we present the first live fonts and evaluate their legibility and learnability compared to other scripts. And to the best of our knowledge, we're the first to propose using animation to differentiate characters in a script. And that second live font is supposed to be moving, but in any case. So Livefonts are part of an already growing trend towards enhancing text through animation. Many platforms already support animated emoji, which appear in line with stationary text. Sorry, I don't know why. I'm not sure why the animations are stopping, but pretend that it's still moving. And many platforms already support these animated emoji. Here's an example from Skype. Other platforms do as well. And as we move away from pen and paper text displays towards screen displays, we have this really exciting new opportunity for integrating animation and color and richer displays into text, which Livefonts take to a new level. And I'd also like to point out that the successful integration of animation in text-based interfaces demonstrates the technical feasibility of Livefonts. Okay, great. So we have this idea of redesigning letter forms and using animation to differentiate them, but how to do this is not clear. The design space is virtually unlimited when we move to screens. So we reached this question: how can we design Livefonts to improve legibility for low vision readers? We'd like to do this in a principled way. Because the design space is so large, to narrow it, we engaged in a participatory design process with low vision readers who are our target users. We showed them a variety of designs, including colored dots, different configurations of dots, and various animations. And ultimately, we found that colored blocks of simple animations were highly legible for our low vision participants. So we narrowed our design space to just that set of possible characters. After we narrowed our design space, we ran a crowdsourced perceptual study to fully explore that narrowed design space. And the goal was to find a set of characters that is highly discernible. So here's a demo of the task that we ran. There's a very small target at the top. I'm not sure if you can make it out. And the task was to identify the color and animation present in the target. There are 11 options for color and 9 for animation, giving 99 possible options on each task. And we made the target very small because we wanted to learn about discernibility at small sizes specifically. So we ran this experiment on Mechanical Turk, where we recruited 50 participants who gave us a total of 5,386 evaluations. This resulted in a 99 by 99 character confusion matrix. So again, each possible color and animation combination constitutes a character. And we formulated the problem of choosing the 26 characters for our alphabet as a minimization problem, where we're trying to minimize the confusability within the set of 26 that we're choosing. And because it's an NP-hard problem, we used branch and bound to solve it in a reasonable amount of time. So here are the 2 alphabets that we came up with as a result of this optimization process. The top one does not involve jumping characters, but the bottom one does, because we wanted to see if the additional vertical space required to render jumping paid off in terms of increased legibility. Okay, great. So now we've got some designs, and we face the question, can Livefonts improve legibility for low vision readers? So do our designs actually work? And again, by legibility here, we mean how small characters can be and still be discernible. And I'd like to point out before we delve into the procedure that we use, that evaluating legibility of scripts that nobody knows how to read is difficult. So traditional legibility tests, which involve asking somebody to read something or identify some characters, aren't possible without training because participants don't know how to read the script. They don't know what the characters are called. So these tests largely don't apply. So we came up with a couple of tasks to evaluate Livefont legibility without training. And one was a transcription task, which is shown here. The other was a scanning task, and I'll refer you to our paper for details on that one. So in the transcription task, participants were shown a 5-character target string, which you see at the top, and they were asked to transcribe the string, character by character, using an organized visual keyboard. So here the keyboard's organized by animation and color to support visual search. We started with a calibration step to adjust the target size to the person's vision, especially because within the community of low vision, there's a large variety of visual abilities and how large the target should be to make it appropriate. And after the calibration, each target was 90% of the previous target in terms of size, so things are getting smaller and smaller, and we cut them off when they reached failure, which we defined as making a mistake on 6 out of 10 characters across 2 back-to-back tasks. And I'd also like to point out that this transcription methodology is a big improvement over previous methods used to evaluate smart fonts, where string matching was used. We had a single string and maybe 4 or 5 options of matching that differed by 1 character. And in a single task like that, you only get information on 1 character that's mistaken. In this, you get information on 5 characters from the whole set of 26 possible entries that people can make. All right, so the scripts that we evaluated were the 2 live fonts that I showed you earlier, one with jumping and one without. The best static smart font, which is called tricolored braille, which we found to be the most legible in previous work. We also included a low vision font called Matilda, which was designed by typographers specifically for low vision readers. And we wanted to see if we could improve even upon traditional tailored fonts. And Latin was our baseline. In this case, we chose Verdana to represent Latin. So we recruited 25 participants. We ran this experiment in lab, which is an improvement over past work, which was done remotely. We recruited 10 low vision participants and 15 sighted participants. And again, past work did not include low vision participants in evaluation, but instead simulated low vision. We had 15 female and 10 male participants, and ages ranged 15 to 67. And this was a study where each participant viewed every script. So we found that Matilda, which was the traditional looking font tailored to low vision, did not typically improve legibility. So if you need to zoom in this much to read text on your phone, you're basically stuck with that if you're using a traditional looking font. We found the best smart font from previous work improved legibility somewhat. It was equivalently legible at about 3/4 the area of a traditional font. So you only need this much space on your smartphone to represent the same amount of text. And our Livefonts provided even more benefit. So version 1, for example, was comparably legible at half the size of Latin. And these results were fairly consistent across sighted and low vision groups. While those were the average results, we had some individual low vision participants that were able to make out our Livefont at even 1/4 the size of Latin, and some sighted participants were able to make out the Livefont at 1/6 the size of Latin. So even though this was a small study, these results are quite exciting. Okay, so our results at least suggest that Livefonts can greatly improve legibility for some people, but this is useless if people can't learn to read these scripts. Which brings us to the question, can people actually learn to read an animated script? So because we're proposing the first script that uses animation to differentiate between letters, this is an exciting question that hasn't been addressed before. To evaluate this, we built a website to teach people how to read Livefonts. The main feature was a set of yes/no questions. All the questions were encoded in the Livefont, but every 10th question was in Latin, which again is the familiar A through Z. We also provided a tutorial, flashcards, and a cheat sheet. And these were crowdsourced questions, typically fun in nature. For example, this reads, do horses have wings? We also provided overlays for our Livefont, where the traditional letter form is placed on top of the new letter form, just to ease them into the learning process, and we gradually removed the overlays one letter at a time. So here, well, it's frozen again, but here the A does not have the overlay, but the rest of the letters do. And this was the same website design and experimental setup used in previous work evaluating smart font legibility, which again are scripts that are not animated, which allows us to compare results. We recruited 15 participants on Mechanical Turk. 6 were low vision and 7 were sighted. And as a side note, recruiting low vision participants on Mechanical Turk is non-trivial because there's no filters based on disability or things like that, so we had to run a separate survey on vision. And participants spent about 2 to 3 hours per day for 1 week learning the Livefont, which isn't a huge investment. And we chose just one of our Livefonts, which was the most legible in the legibility study for this evaluation. So overall, we found that our Livefonts are comparably learnable to non-animated scripts. Here, I've provided the results from our previous evaluation using the same experimental setup for smartfonts, which again are non-animated scripts. And this shows the average speed at answering the encoded questions after 2,000 practice questions relative to Latin. So a value of 1 would mean they're answering encoded questions at the same speed as Latin. A value of 2 means that they're twice as slow, and so on. So in prior work, we showed participants generally achieved speeds between 2 and 7 times slower than Latin with 2,000 practice questions. And they typically started at around 25 times slower than Latin, so they did make a significant improvement throughout the week. In this work, we found that participants achieved comparable reading rates with 2,000 practice questions. You can see for our cited group, they were about 3.4 times as slow as with traditional letter forms, and with our low vision group, about 4 times as slow. And I'd like to point out that while twice as slow or 4 times as slow might sound kind of bad, these are just the averages for the groups, but there were individual participants who did much better. So we had 2 of our 6 low vision participants who just about reached their Latin reading rate at the end of the week, and 3 of our 7 cited participants either reached or exceeded their Latin reading rate after the course of a week. And there's a possibility that if people kept learning these for longer, that they'd do even better. So the main takeaway here is that Livefonts seem to be comparably learnable to non-moving scripts, but also provide a legibility boost. All right, so in summary, the problem that we addressed is reading small, blurry text, which is a big problem for low vision people using personal computing devices. The solution we proposed are Livefonts, which are alternate scripts for English that redesign each letter using animation to differentiate letters from one another. We addressed a few research questions along the way. How can we design Livefonts to improve legibility for low vision readers? We provided a principled method to do this involving participatory design with the low vision community and perceptual tests that were crowdsourced. Then can Livefonts improve legibility for low vision readers? We provide some evidence that suggests, yes, for some people it can. And can people actually learn to read an animated script? And again, we provide some evidence that, at least for some people, these types of scripts are quite learnable. Future work includes personalizing these scripts for individual users because you can install them on your own devices. There's this exciting opportunity for personalization. We like to expand beyond A through Z to account for punctuation, digits, and other characters. Larger follow-up studies to hopefully confirm the results we've shown here. A longitudinal evaluation to figure out what happens if people are using these for months or years. Can we improve our reading speed, for example, over what we do with traditional letter forms? Exploring other teaching methods, so I briefly mentioned the overlays that we use to help teaching, which actually did ease the learning curve quite a bit. And there could be other teaching methods that would help even more. And exploring the design space further. The design space is huge, and as we're moving to use the capabilities of screens for text, I think there are a lot of exciting design questions to explore. All right, so thank you very much.
Hi, Wendy Mackay from INRIA and Université Paris-Saclay. Very nice work, I really like this. I have a couple of questions, if nobody else lines up behind me. The first question is about issues of colorblindness, because there's a lot of red, green, and blue, yellow colorblindness and so on. So did you take that into account in the design of the Livefont?
So in short, the answer is no. But that's a great point. You know, in future work, it would be great to consider different people's color perception and perhaps make different versions of the font for people with different abilities.
And then the second one is sort of related. So I noticed, for example, that you use the S as the red spinning thing, which is a very salient one, easy to remember. But S is one of the, it's sort of a low information letter in the sense that you're making it plural or something. So did you think about how so animation is drawing your eye? How did you choose which letters get that sort of extra jolt of animation?
Yeah, so we chose the assignment of characters to letters to help people remember them better. So like you're saying, the S is spinning, and I think the O was orange, and the P is pink, and things like that. But for future work, it would be really interesting to try to optimize the assignment of animations to individual characters based on people's perceptions, but also letter frequency or bigram frequency. There's a lot of exciting work that can be done.
Great. Yeah. Thank you.
I had a quick question before we move on, because we have to wait for the video to show up. So do you think it's a problem that it's a font that cannot be printed?
Potentially, yes. I mean, in the long term, I imagine that we could have paper that supports animation, right? Or, if your vision is bad enough, you probably have to rely on devices where you can use zoom, because, maybe using a magnification device isn't enough. So, I mean, yes and no, I guess.